Okay, folks, in our final video here, this is a video that's going to focus more on the flight duration aspect, especially after your rocket hits apogee. We're talking about the deployment of a streamer or a parachute. In the video that you originally used to design your Estes Alpha, the gentleman had you use a parachute and no modifications were made. So now we can modify. So let's first take a look at the data. I'm going to come up here to flight simulations. And if the B64, let's just use this right now as our data here. I'm going to hit run simulation. Okay, so currently with a B64, we have an apogee of 399. The flight time is 33.5 seconds. Okay, so the question is, depending on the problem that you were given, do you need to increase or decrease your flight time? As we mentioned, getting to apogee, you can see took only 5 seconds. It then took a remaining amount of time to then come down. Okay, so if you do the math there, it took about 28 seconds from apogee to then come down and hit the ground. Okay, 28 plus 5 is roughly going to be 33. Okay, now keeping that in mind, okay, we can control apogee with either an engine and or the mass and or the way we design all the pieces and parts. But after we hit apogee, this is now controlled by your recovery system and yes, the weight of the rocket. Depending on the weight of the rocket, that also has an effect on how quickly it's going to drop. Got to take that in consideration as well. But once again, the recovery device is going to be a big part of this demonstration. Let's go back to rocket design here. Remember, 33.5 is our current duration here. Let's go ahead and take a look at the parachute that was originally put in with the demonstration that was used earlier on to make this rocket. So let's go to parachute. Here we have diameter. And I'm going to be honest with you, I wouldn't manipulate really much of anything here but the following. Okay, number one, diameter. Okay, and as we mentioned, you can hit up or down, and this usually does increments of 1. So I started off with roughly an 11-inch or 12-inch diameter. Let's just say I double it. Let's just say go to 24. Okay, so I'm going to hit close. Okay, I'm going to go ahead and go to simulations. Remember, 33.5 was the original. If you ever see a red circle, it means you've made changes and you have yet to update the simulation. So I'm going to click on the simulation. I'm going to hit run, 33.5. Let's see what happens. Of course, 44. Made the diameter twice the size, but that increased by about 10 seconds. Okay, once again, I can go to plot export. I can hit plot, and you can see here, okay, now this is something that's kind of interesting. Just after apogee, look at that. I've made some adjustments through my last few videos. So you can now see something I referred to way back in one of my earlier videos. Apogee is happening first, and the recovery system is coming out just after. Okay, that ideally that's good. I like that. And then it's going to take longer to come down because I've increased the diameter of the recovery system. Okay, so I've actually gone 10 additional seconds because I went from a 12-inch to a 24-inch diameter parachute. Okay, so let's go back to rocket design. Let's open up the parachute again. Once again, I want you to keep this very simple here. Diameter is probably the only thing I want you to change. The drag, number of lines, the line length, okay? Of course, some of this could be done with a little bit of experimentation, which is the length of your shroud lines. Those are the pieces of string that connect the parachute then to the shock cord. You could obviously make these a little bit longer, increase or decrease, but at the end of the day, folks, at the end of the day, the diameter is probably going to be our main focus. I'd be not wanting to really change anything else. Material obviously can have an effect, and I don't mind a student changing to some other type of material. You're not talking about increasing any type of mass significantly here, but for right now, it's just using good old-fashioned ripstop nylon. just more like just leave it there and just focus on the diameter. Okay, now it does tend to kind of max out at 60. If I were to type in a number like 70, let's just see what happens. Okay, it looks like it's taking that. Okay, interesting enough. But let's go ahead and return this back to that 24 inch. Okay, and remember, that's probably the best way to do is just type this in. Now, remember, every time you make an adjustment, let's take this down. Actually, we had 12. Let's take this down to 6. And here's something I'm glad I'm making this adjustment here. You know, this is not just a number, folks. A recovery system is just that. It's recovering the rocket so that the rocket is not damaged upon impact. So, you know, 12 inches is probably an ideal diameter for a safe landing. If you're getting below 12, it's going to come down faster. So we just got to keep that in mind. So I'm going to hit Run Simulation. I'm going to hit Plot Export. Now look at the difference. I went from a 12 inch to a 6 inch, which honestly, folks, that's not much of a recovery system. And what you're looking at here is this thing called ground hit velocity. It's still coming down at a fairly decent rate of 27 feet per second. Remember, that's per second. I usually tell kids when we make Pringle chip rockets to try to keep this under, if you can, under 20 feet per second, because anything above that is going to hit the ground with much more impact and probably damage your rocket. Okay, so let's just be careful. I know we're trying to solve a problem here, but let's also be a little realistic with the fact that if this were a real rocket, you'd probably end up damaging the rocket. So that's, obviously it's coming down in less time, but once again with much more velocity as it's dropping because the diameter of the chute is much smaller. So we have to be careful with that. Once again, I don't recommend probably anything above a number like maybe 20. Now, once again, you can teeter-totter around it, but just be very careful. Okay, let's try to stay realistic here. Now, be careful if you decide to use something other than a parachute. Let's say you want to use a streamer. Okay, first things first. Okay, don't have a streamer and a parachute. So let me take my parachute. I'm going to hit delete. Remember, Control Z can always bring things back, or you can just add the parachute again. Click on the body tube, and you might be looking somewhere here, and now you need to scroll down. Okay, scroll down to the bottom. There's my parachute. Let's now look at a streamer. Okay, now this will automatically put things where it thinks it needs to go, but in all honesty, that's a little bit too close. So if we look at the location of this, we want to kind of make sure that it's roughly where we want it. Okay, so if we look right here, I can click this number, and this is moving it down. And I kind of want to keep this obviously a little bit more towards the top of this tube. There's that coupler, so probably this general area where I have it right now is probably not too bad. Okay, maybe somewhere in that general region right about there is probably pretty good. Okay, this is not going to have a significant change in CP and CG because these things are so light. Okay, now once again we go back to length and width. So here you have two variables that can be adjusted. There's this thing called strip area where I've noticed if I increase this, it kind of keeps things proportional here. I kind of like that because I can basically increase both the length and width at the same time, and I'm giving myself a proportional. So you wouldn't have like a 40-inch long by 1-inch strip. It's kind of saying, okay, 40 to 4. Okay, so it's keeping it proportional as I use this thing called strip area length. Okay, excuse me, strip area. Okay, now I'm going to go ahead and just really bring this up. Let's just max this out at 62. Why not? Okay, and I'm not going to worry about anything else here. I did kind of move the streamer a little bit more in position. I'm going to hit close. Okay, once again, my stability doesn't really change much here, but what's going to change, if anything, is my flight duration. Okay, let me hit close. Remember, you make changes, flight simulation. Let's go to a C6 this time. Originally this had a 57-second flight time when we had a C6. Let's just see what happens now with this streamer. Let me hit run simulation. Okay, wow, this is coming down faster. And remember, this originally was using a 12-inch parachute originally. And then I went to this streamer. So we can see streamers do bring the rocket down at a faster rate. Now remember, wow, be careful here. Okay, just be careful. We're definitely getting well above 20. This is coming down with quite a bit of speed. We'd want to be very careful with that if this were a real rocket. And you know, I'm making this video right now, and I'm thinking about what I'm telling you, and I know we're doing this through distance learning, and I know we're making a rocket that in turn will not be built. But let's just try to be a little bit realistic with how quickly these rockets are descending. Okay, so here we have once again. Blue line is the recovery, the green is the apogee. They're happening almost neck and neck, but look at how quickly it's coming down. It's coming down with a bit of velocity here from apogee at about 700 and maybe 25 feet. It's coming down rather quickly here because it's using a smaller or better yet a recovery system with less surface area. Okay, now streamers have their moment, just like parachutes do. So depending on the problem that you're given, a streamer might be a good choice. Parachute, not both of them together, please. It's one or the other, and that's the only two options we have. Now, let's try that same streamer. Remember, we originally had a 6-inch parachute, which I don't recommend. 6 inches is kind of small here. Let me hit run simulation. Okay, this is actually coming down fast. Look at that, it's coming down faster. So let me go ahead and hit plot export. Okay, let me go ahead and hit plot again. Okay, so once again, I know I said 20 ideally, but I'm going to obviously give you all some flexibility with your descent velocity, your ground hit velocity. So just be very careful here that this thing is not coming down like a freight train. It's going to smash and obliterate your rocket if it's coming down too fast. I may have to do a little bit of research on this and either add something to this presentation and or talk about it more in class. Okay, all right, so ladies and gentlemen, that was our recovery system, and I'll leave you with one last little piece here because I know someone's going to ask me, can we add mass? Just wait. The answer is you can. It could be added to the nose cone, to the body tube, and or to the booster section body tube. And it's just a component that when you add it, you tell it how much it's going to weigh. Okay, now once again, experimenting with this, okay, goodness gracious, you'll see a lot of change with apogee and stability. So we have to be very careful, but I think it is fair enough to say that on real rockets, students, teachers, hobbyists, they use mass when they need to fine-tune a rocket because it's not going, it's overshooting its target and they're finding ways to bring it down. I'll leave you with this though. What you have to be careful is not so much just the weight. The weight is very important, but it's also the location of the weight. Location of the weight, okay? They do have this mass type called unspecified. You don't have to really pick anything here. Just leave it as unspecified. You can adjust it. You can even click here and change it to grams. You can change it to, obviously, I wouldn't go anything probably above ounces, but grams is good, possibly ounces. Approximate density, the length, you can see you can change the length. I probably wouldn't worry too much about the length. Obviously, the diameter should not be bigger than the rocket, but really these two things are significant. This is the most significant, mass. Now, where it's located is once again what's important. Look, if I shift it towards the back, now remember, you can't put a mass on top of a motor. It'd have to be either somewhere. Let me take that back. You could put mass more towards the back of your rocket. You could. It could somehow be fit somewhere in this general area. I've seen it. We've done it before. Look at how the stability changes. Look what happens when I move it all the way to the top of the tube. Okay, it's becoming overstable. Less stable here, more stable here. Okay, now remember, I'm going to finally go all the way up to the top. Okay, right in the nose cone. Overstable. Okay, so in relation to the rocket, location. And really my apogee hasn't really changed much. What's really changing more than anything is the stability of my rocket. So once again, adding a mass is allowed. Be careful with this number. I could just see a student accidentally hitting kilograms and not realizing they added 1 kilo, 1 kilogram, okay, to the rocket. And if I do that, look at this apogee here. Watch this. 0.008 feet. Yeah, you're launching a bowling ball along with your rocket, folks. Good luck. Okay, you're not going anywhere. So once again, grams is good, ounces is good. Okay, but let's be realistic. Just to give you a sense of weight, a Pringle chip, a real Pringle chip, is a 2 grams. That's how much a real Pringle chip works. 2 grams. So just be very careful with how much and where it's being added. Okay, but you may add, once again, what's called a mass component. Okay, guys and girls, that's the last and final video on recovery systems and adding a mass component. Good luck with the challenge. Once again, remember, Control Z is always something you can use to go back. You also saved this file, so you have an original Estes Alpha rocket. And don't forget the file name. We saved this as your last name, period number, and then I just threw in open rocket. So this will once again be what you turn in when the assignment is due. Okay, good luck.